Hello students, welcome back. Let us resume our discussions on eigenvectors and eigenvalues. This time, our focus of attention is the characteristic equation. What is characteristic equation? Here we go. This is how you find the eigenvalue. So, the root of characteristic equation turns out to be an eigenvalue, and from that eigenvalue, we can find out eigenvectors. We went through an example already. Oh, by the way, this is a definition of the eigenvalue and eigenvector. Okay, I want you to open this cell as a matter of fact. Here's an example problem. Given eigenvector, find out an eigenvalue. This is just too trivial, so trivial that it's not really worthy of our time. Calculate AV, we get the answer, and compare it with V, and we get the eigenvalue. Too simple. This one is a little bit more challenging and worthy of our consideration. Given eigenvalue, how do we find an eigenvector? We set up AV equals lambda V, where lambda is equal to 2 in this particular case, and V is xyz because A is 3 by 3. If A had been, say, 10 by 10, then we're going to get x1, x2, x3 all the way over to x10, and we're going to get a system of 10 linear equations. More complicated, yes, but they're all elementary and just tedious. Computers can handle all those, no problem. So basically it's this. From the characteristic equation, we get the zeros, which are the eigenvalues, and from each eigenvalue, we can find out eigenvector. Now we get a linear combination of those eigenvectors, then that's going to be the general solution. Roughly speaking. There are of course exceptions with the duplicates and so on, but roughly speaking, that's a kind of roadmap. But here's a missing link. Why? Why is this giving us the eigenvalues? Here is the definition of the eigenvalues and eigenvectors. L of V equals lambda V. That's one thing. And determinant equation, that's another. How are they related so that the solutions of this characteristic equation turns out to be the eigenvalues? Let's answer that question, and that's the final piece of puzzle. All right, let's go. And this is a theorem. Let V be a vector space and let L be a linear map from V to V, so it's a linear operator. Then a scalar lambda is an eigenvalue of L if and only if L minus lambda I is non-invertible. In other words, like this. A scalar lambda is an eigenvalue of L if and only if this operator, L minus lambda I inverse, does not exist. Or this one, L minus lambda I is not invertible. Now, what do you mean by non-invertible? It turns out non-invertible means determinant is 0. So lambda's eigenvalue of L is equivalent to this. If we prove that, then non-invertibility is the same as determinant being 0, as we saw before and proved in linear algebra class. We have this equivalence. Lambda is an eigenvalue means in place of t we have this lambda, so lambda is a solution of the characteristic equation. So all boils down to this. If we prove this equivalence, then everything is fine. Okay, go ahead with the proof, and it's not going to be that simple because this is if and only if. We have to prove two different directions. First, if lambda is an eigenvalue of L, then we have to prove this. So basically this. No, let's keep it at if and only if, by the way. So what do you mean by lambda is an eigenvalue of L? Just by the definition is this. L of V is equal to lambda times V for some non-zero vector V. So for some non-zero vector V. That's what it means by an eigenvalue. You see, here's the definition. Here, this for a non-zero vector. If that vector exists, if that non-zero vector exists, then it's called eigenvector, and this lambda is called an eigenvalue. So that's basically what this thing is all about. And what do you mean by that? From here, you're going to do this. Flipping over to the other side, we're going to get, flipping this over to the other side, we can write like this. And then we can combine all these like this. L minus lambda I of V is equal to 0, and that's what we are getting. So, can you get non-invertibility there? What if this is invertible? Then if I flip this one over to the other side, then you're going to get V equal to 0. You see, if this inverse exists, then we can flip this over to the other side by multiplying the inverse and kill it. So V equal to 0. We can always cross this thing out. If it is non-invertible, we cannot cross it. So that is the key observation here. Make sense? I don't know if it makes sense or not because it's a complicated concept, but here it is anyway. So assume lambda is eigenvalue, there is non-zero vector, eigenvector, so that L of V is equal to lambda V, alright, that's the definition. And here's a key step. Suppose that inverse exists, and we are trying to draw a contradiction. Then, under these assumptions, now we just apply the algebra. L of V is equal to lambda V, and then apply the algebra. Flip this to the right-hand side. L of V minus lambda V is equal to 0. And then combine those, factor V out, basically. L minus lambda I of V is 0. And then finally flip it to the other side by taking inverse. So we have V equal to 0, and that contradiction because V is supposed to be an eigenvector, so it's a non-zero vector. So if you look at it like this, it looks simple, but when you try to build it out of scratch, it wasn't really easy to understand, right? If you look at it like this, it looks simple. It's a kind of illusion, as a matter of fact. It's not simple. How about the other direction? Actually, this is worse. So let's start from here. What do you mean by that? Non-invertible. That means L minus lambda I is not one-to-one. It's not a one-to-one function. And in linear algebra, we established this. Not one-to-one means kernel is non-zero. Kernel of this thing is non-zero. So one-to-one map being equivalent, the kernel is just 0 and nothing more. And we could prove it directly, or we could use rank theorem, but that's all about linear algebra. And this too sounds too much like linear algebra, but we started, so let's finish it. So we get up to here, and from here we can make this observation. What do you mean by kernel? Kernel means a certain vector applied with this linear map will give me 0. That kind of vector belongs to kernel. So basically this is 0 vector, yet you see, kernel is non-zero, so there's vector v other than 0 vector that does this. And that is a key observation. And then from here, if you break up and then do your linearity computation, you can prove that v is indeed an eigenvector. That was the setup. Was it easy to follow? Probably not. Okay, here's the elegant form of the answer. Let's suppose L minus lambda I is non-invertible. Therefore, kernel is non-zero. So what do you mean by kernel is non-zero? There is something other than 0, like v, other than 0 vector, so that v times this is 0. Ooh, actually there's a typo here. Sorry about that. So L minus lambda I of v is equal to 0 vector. Once you get that, from this point is easy. So from here, break up, and then flip this to the other side. There you go. We have the eigenvector v. It's non-zero vector, so it's eigenvector. So lambda is an eigenvalue. If you look at this proof, it looks simple. Simple and elegant. This idea, and then from here, just simple algebraic manipulation. But as you saw before, it isn't easy actually. If we tried to set it up from scratch, it wasn't easy at all. But in the end, it comes out like this. So as a conclusion, if lambda is an eigenvalue of L, lambda is an eigenvalue of L if and only if this linear map is non-invertible. So determinant of this is non-zero. So determinant of that, we call it a characteristic polynomial. And then set it equal to 0, we get characteristic equation. So lambda is an eigenvalue of A if and only if lambda is the 0 of the characteristic polynomial or the solution of the characteristic equation. So that completed everything. Well, I take it back. It's not everything. We skipped a lot of things here, especially about determinants. Invertibility is equivalent to determinant being equal to 0. Those kind of things we didn't prove actually. Our textbook author does not prove that either. As a matter of fact, you'll have to go to linear algebra, and we spent about a month establishing it. Okay, so much for all those non-essential topics from chapter 8. And let's meet again in chapter 9. And chapter 9, the earlier part of chapter 9, or module 14, is going to be for everybody. That's the essential part. Module 15, on the other hand, that's going to be optional.